Alright, so now that we've covered this, and yeah, we're done this problem, now let's jump right ahead to problem 22. And this one states right-angled triangles are constructed as in the figure. So you have point P there, so you have point P, and now you have a right-angled triangle. In this case, length 1, and then this opposite is 1. There's a right angle. And then it extends outward, so this doesn't have to be 1. And notice how the next hypotenuse becomes the base. This is the base, 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 etc. Alright? And each triangle has height 1, so that's the height. And its base is the hypotenuse of the preceding triangle. So if this one right here is the hypotenuse, it becomes the base for this one here. And it is the hypotenuse of the preceding one. And show that this sequence of triangles makes indefinitely many turns around P by showing that the summation of this angle, this theta sub n, is a divergent series. In other words, it can turn infinitely amount because the angle keeps getting bigger and bigger that you're rotating around. Alright, so now let's take a look at the solution. And solution goes from here. So suppose that the base of the first triangle has length A. So let's say instead of 1, let's say it's A. So that base. And then by repeated use of the Pythagorean Theorem, we find that the bases of the successive right angle triangle are... Alright, so let's start here. Let's say we have a triangle. Make a table. Alright, so we have triangle and then we have the base. I'm going to put like this. That's triangle number. And then this is our base. Alright, so that's the base, is the hypotenuse, is a hypotenuse of the preceding triangle. So each one. So let's say we have, this is triangle 1. So this triangle 1 here, and then the base is A. Instead of this, they just put an A in the solutions manual. So A, and there's the opposite is 1. So then we could solve for the hypotenuse there as using Pythagorean Theorem. So, but first we have the base there. Then triangle 2. Yeah, so triangle 2 is, this is the new A. Or yeah, this is a new base right here. So this is the new base, and this is the hypotenuse of this. In other words, B is equal to square root of 1 plus A squared. A squared, yeah, 1 squared plus A squared, etc. And this, because this is our A. And then we can keep doing that as well for the new base, new base, new base, and it's always the hypotenuse of the preceding one. So this becomes square root 1 squared plus A squared, which equals to, well, square root 1 plus A squared. And now the third triangle is going to be, well, instead of squaring this A squared, this is the new base. So this becomes, again, it's going to be another 1 squared because all the heights are 1. And then plus, I'll put this plus this one here squared. And that's going to be, I'll put this whole thing like this. Square root of... And then, oh, squared as well. So squared of the square root 1 plus A squared, like that. And then square roots cancel, because if we're squaring it. This equals to, well, 1 squared plus 1. Yeah, this is 1 squared, that's just 1. Plus 1, and then plus A squared. Well, the 1 squared is just 1. So then this just becomes 2 there. I'll just add those up. So 2. I'll just keep this for completeness. This equals to square root 2 plus A squared. And then if we do the next one here, the fourth triangle, we'll use this as the base. That's a new base. So it's, again, we're going to get a 1 squared. So I'll just leave that 1 by itself. So yeah, we'll just keep it like that. 1 squared is just 1, which is the height, plus this squared, which is just going to be 2 plus A squared. Because we cancel out the square roots when we square it. So in other words, this equals 2, 3. So you can see the pattern now. So this first one is A. Yeah, the first triangle base is A. The second is going to be square root 1 plus A squared. The third is 2 plus A squared all square root. And the third has a 3. So there's 1, 2, 3, and so on. And then if we continue all the way down, I'm going to make this longer down. Make this down, and then dot, 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 all the way to the end, dot, 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 all the way to n, we get this becomes n minus 1 plus a squared. Yeah, so n minus 1 plus a squared, and where, yeah, so this n minus 1 is always one less. So if this is 4, this is 3. So if this is 3, this is 2. So this is n minus 1. And now for completeness, let's just get the nth triangle. So this is the nth triangle, and let's just draw it out and get the hypotenuse like this. So nth triangle is going to look something like this. Let's say there's the point P, and it goes like this. Let's go over here. So we know the base of it is the hypotenuse of the previous triangle. So this is P, and this is right angle, like this. Let's do a right angle, better one. So here, just fix that up. So that's a right angle. We know that's the height 1, and then this right here is going to be our n minus 1 plus a squared, and this angle right here is our theta n. And now this hypotenuse, this h, is, I'll just solve this one, it's going to be square root of 1, the side, plus this over here, that's going to be plus n minus 1 plus a squared, because yeah, the square roots cancel. This equals 2, this cancels, we're just left with a square root n plus a squared, like that. So that's our h. And now what we could do is, well, let's write this this angle in the function. Well, we know that the tangent of this is, so thus tan of theta n is equal to opposite over adjacent. That's just equals to 1 over adjacent, which is square root n minus 1 plus a squared. And then we could just take the inverse. In other words, theta n is equal to tan inverse of that ratio. So 1 over square root, square root n minus 1 plus a squared. Because remember, we want to see the summation. This goes to infinity. Alright, so thus we wish to show that the following series diverges, basically the summation of this this angle right there. So what we'll write is the summation of, or summation from n equals to 1, because we'll start from the first angle. So n theta sub n, so in other words theta 1, this equals 2. So we have to show that this diverges. So this summation from n equals to 1 up to infinity of inverse tan of this giant number, or I mean this giant fraction right here. Let's write this as 1 over square root n minus 1 plus a squared, then all bracket. Alright, so instead of having this n minus 1, because note here that the only n variable is over here, n minus 1. At n equals to 1, we get n minus 1 equals to 1 minus 1 equals to 0. So it starts off at 0 at this phrase. So we can get rid of that by starting at n equals 0. So this just changes it, just make it neater. So we'll write this as, and get rid of that negative 1 there. From n equals to 0 up to infinity of tan, inverse tan of 1 over square root n, just square root n minus, plus a. 1 over square root n minus plus a squared, like that. So it's the same thing. So at n equals to 0, this just becomes 0. At n equals 1 on this one, this becomes 0. So, and then you increment sequentially, 1 by 1 each time, so it's the same thing. Alright, so we wish to show this converges, but we'll first notice, because it's a bit complicated with this inverse tan and then 1 divided by square root n plus a squared. So first notice that the following series diverges by the limit comparison test. In other words, if we take a series of this inside function, this 1 divided by n, 1 divided by square root n plus a, this diverges by the limit comparison test, because, well, if we got rid of this a, then it was just a p series where p is equal to square root, or 1/2, and that diverges. So what we could do is, well, first notice the limit comparison test. Let's recall this. So recall from my earlier video, the comparison test is, suppose that summation of an and bn are series of positive terms. If the series bn is convergent and all the terms an are less than or equal to bn for all n, then the series an is also convergent. And likewise, if this is divergent and an is greater than bn, all the terms, for all n, then an series is also divergent. So that's a regular comparison test. Just to recap, and now the limit comparison test is suppose that the series an and bn are series of positive terms. If the limit as n approaches infinity of an divided by bn equals to c, where c is a finite number and c is greater than 0, then either both series converge or both diverge. So what we'll do is, so in our case, we're going to compare the series with that inside term, compare the summation from n equals to 1 up to infinity of 1 divided by square root n plus a squared. So compare that with something we know that either diverges or converges, or in this case diverges. Summation n equals to 1 of 1, this is a square root 1, oh yeah, square root 1 over square root n. And this is a divergent series. This diverges. Yeah, this is a divergent p series. Remember, p series, the harmonic series is where p is equal to 1. And this is the divergent p series, in other words, p is equal to 1/2. And this is less than or equal to 1. And if it's less than or equal to 1, then it's going to be divergent. And here I just quickly teleported to the earlier part where I mentioned this. So the p series, summation from n equals 1 to infinity of 1 divided by n, p is convergent if p is greater than 1, and divergent if p is less than or equal to 1. Yeah, so it's divergent for this. It's only convergent if p is greater than 1, and divergent for all other cases. Alright, so that's teleporting back here. So we know this is divergent, and now what we'll do is we'll take the limit comparison test. So we'll take this an over this bn right here. So let's take that test right now. So thus, let's put thus limit as n approaches infinity of the an term is this, the one we want, and then this is the comparison one, the bn. And then an is, let's just write this here, 1 over, I'll put this like this, 1 square root n plus a squared over 1 divided by square root n, like that. And then whenever you're dividing by a division, this just goes on top. So then this becomes equals to the limit as n approaches infinity of square root n over, let's put this better, square root n over square root n plus a squared. So that those ones go down there. And now what we have is, yeah, these are all square root. We can just combine them all together into one giant square root. So this equals to limit as n approaches infinity of square root n over n plus a squared. And then what I'll do is times the top and bottom by 1 over n, and then 1 over n, so that we don't have an infinity over infinity situation. Now this equals to, let's see, where should we put it? I'll put it right over, I'll put it right over here. This equals to limit as n approaches infinity of square root, and then the top becomes 1, the bottom becomes 1, then this one becomes a squared over n, like that. And then this part right here, this approaches 1 over infinity, which approaches 0. So then this equals to, well, this is equals to square root 1 over 1 plus 0. Which equals to, well, just squared 1, everything's just 1, so it just becomes 1. Like that. Alright, so this, limit equals to 1, and if we recall here, so it equals to c, 1 is a finite number, and it's greater than it's greater than 0, then either both series converge or both diverge. So this is greater than 0, so in other words, since this series diverges, this also diverges, because by limit comparison test, they both be the same thing. Thus, summation from n equals to 1 up to infinity of square root n plus a squared also diverges. Like that. And now we can apply the limit comparison test again, but this time with our original series. So the series we want is this right here. So we'll compare this with this one right here. Alright, so let's compare that. So we're going to compare So I'm going to compare, I'm going to write the whole thing out. So summation from theta right here, this is up to infinity from n equals 1. This equals to what we had solved it. Summation from n equals 0 of right here, the last one we had was inverse tan, and then 1 divided by a square root n plus a squared. Then this is going to be inverse tan, and then 1 over square root n plus a squared, like that. And we are going to compare that with the series we just solved over here. So compare that with a summation up to infinity, and we can start from 1 in this case. Start from 1 right here, n equals to 1 of this top part right here. No, I mean not 1. We can start from 0 here. Let's just start from 0. It doesn't matter if we start from 0 or 1. It's still going to infinity. So this one, so it matches up with this part right here. So this is going to be 1 over square root n plus a squared, like that. So we know that this is divergent from earlier. So we know this is divergent from limit comparison test. And now we're going to do limit comparison test again. Thus, limit as n approaches infinity of an, our new an is this. So that's going to be tan, inverse tan of 1 over square root n plus a. I'll divide this by, and then this is going to be 1 over square root n plus a squared, like that. And we can simplify this by, I'm going to let this, let z equals to 1 over square root n plus a squared. So then, in other words, this will equal 2. And now, this is the same thing as writing, well, limit as n approaches 0. I'm going to write from the right side. This is from the right side. So terms are positive. And then this is going to be inverse tan of z, like that, over z. And this is because, well, as this goes to infinity, we get a setup where this is approaching 0. I.e., z is approaching infinity. Z is approaching 0 as 1 over n plus a is, or I'll just do that here. Note here, note as n approaches infinity, then 1 over square root n plus a, you're dividing by infinity, this approaches 1 over infinity, approaches 0. In other words, z approaches 0, and it's from the right side, because all the terms are positive. Positive, like that. And then this right here, well, this equals to the scenario of, well, this is, as you plug in this 0 plus, you're going to get a tan, inverse tan at 0 divided by 0. So you get a 0 over 0, which is indeterminate. So we could use L'Hopital's rule. Indeterminate, like that. And just sort of recall on tangent, inverse tangent, recall. So we had earlier, but just again recalls for this question. So if we have, if this is theta, this is y, and let's say we had our tan, this is tan. So this is our tan theta, is that 0? Yeah, and so that's our tan theta. Now our arctan, or inverse tan, is going to be something like this. So if this is pi over 2, draw this better. Here, this is pi over 2. This is negative pi over 2. So instead we're going to go, so in this 0, 0, basically we switch the x and y, so 0, 0. Let's do this again. This is pi over 2 at this point. Then you're going to flip it around. So this pi over 2 is 0, so we're going to go 0, pi over 2. And for the red one, I'll draw this in red. So then this is going to be, the asymptote line is going to be across here. This is pi over 2. And this is negative pi over 2 is 0. It's going to be now over at the bottom. Yeah, draw it over here. This is going to be at negative pi over 2 at the bottom. And then as this is going to pi over 2 infinity, instead it's going to go to infinity and pi over 2. So it's going to go like this. And then this one is 0, 0, still 0, 0. And it's actually below it. Like that. And likewise, it's going to go all the way across there. So, and this is our tan theta, inverse tan theta. And go back to here. And this, again, I'll write this over here, nicer, tan theta. So in other words, at this point is 0. So both these are 0 there. All right, so let's block it out. So again, it's approaching 0 here. So 0, 0, 0 over 0, it's indeterminate. So what we'll do is, and I'll also put it over here, 0 over 0, like that. So it's 0 over 0. So then now we could just solve L'Hopital's rule. So using L'Hopital's rule, I'll put this equal sign. So this limit right here is equal to, I'll put it all together here. So we're going to go limit as z approaches, as z approaches 0 from the right side of tan, inverse tan of z divided by z. Again, at 0 over 0, this equals to, equals with the L'Hopital's on top, so take the derivative. And the derivative of tan, inverse tan, recall is just going to be 1 over 1 plus z squared. Now, I'll recall this in my earlier video. So then the derivative of z is just 1. So in other words, this just equals to that. And then when you plug in 0, that just becomes 1 over 1 plus 0, which equals to 1. And this is also greater than 0. Yeah, so thus by the limit comparison test, then this has to diverge as well. Because this is divergent, this has to be divergent, again, as per the limit comparison test. And C is a finite number greater than 0, then either both converge or both diverge. So then they both diverge. Yeah, so that's greater than 0, thus, so we could put this all together, thus the series, which is again all coming back at the beginning, summation from n equals 1 up to infinity of the angle theta sub n is a divergent series. So in other words, it's going to rotate forever, like that. So you're going to have infinitely number of turns around this triangle setup here. So going back up here, so this is going to, when you sum it all up, it's going to go to infinity, like that. All right, let's erase this and continue to go further. And just a note here, so recall the derivative of inverse tan of x from my earlier video. So this is that derivative there from my earlier video here. So d over dx of inverse tan of x is equal to 1 divided by 1 plus x squared. So that's that derivative there.